Hello. Today I'll be going over the Physics 2211 lab number 1. So what are the key concepts in this lab? Newton's first law, an object in motion tends to stay in motion unless acted upon by an outside force. We're assuming no outside forces, so there's constant velocity. Newton's second law, the force on an object is equal to the object's mass times its acceleration. So this is important in the push because the acceleration of the marker from its rest state is equal to the force of the push divided by its mass. Newton's third law, for every action there's an equal and opposite reaction. So us pushing on the marker has an equal and opposite reaction of the marker moving. And there's a few assumptions that we need to make, that there are no outside forces, i.e. gravity and air resistance, acting on the object, and that the object moves only in the x direction. So what are some important formulas? The velocity update formula is important. In this case, Vf equals Vi plus F net over m times the change in time. And because we're assuming that the net force is 0, we can say that the velocity, final velocity that is equal to the initial velocity. And here's the code version. With the vector being 0, 0, 0, that vector being the force vector, because the force is actually 0 in our case. We're also using the position update formula. The final position vector is equal to the initial position vector plus the average velocity times the change in time. And in this case, we can say that the final velocity is equal to the average velocity because there's no change, because there's no net force. And here is the code version of that. We can just use the ball's velocity times the change in time to change the position vector because the velocity is constant. So what's the purpose of this lab? We really want to compare data from real-world experiments of constant velocity and a computational model that we can create using code. And if the two are accurate, then they should align, having the same change in distance vector over the same amount of time. So here is my system/free body diagrams and initial conditions. So the system in this experiment is the marker that we have moving at constant velocity, and its surroundings is everything else in the universe. The initial velocity of the marker is about 0.263 meters per second based on the tracker data. And because we're assuming that the velocity is constant, this can be calculated using the displacement over the time. We are also assuming that the net force on the marker initially is 0. We also set the initial position vector in the code a little bit behind the y-axis because the tracker data has it there. And here's my free body diagrams. So what was the actual experiment? So the actual experiment entailed us pushing a marker across a table and recording the marker in view of a meter stick. This was important because when we uploaded the video into Tracker, we calibrated the tracker using the meter stick, making the meter stick 1 meter, and then going frame by frame for 25 frames to determine the distance that it traveled and how long it took to travel this distance, with each frame being about 0.033 seconds. So here's the code portion of the experiment. So first we copy pasted the starter code, and then using the data we obtained from the tracker data input, we input the data into the starting position, being the initial position vector, as well as the initial velocity vector, which was our average velocity. We did that by finding the displacement over the time. Yeah. And then here's 2 videos of our and the running. And then there's some of the data. You can see that the graph is linear, meaning constant velocity. So what were the results? Results were actually quite promising. We saw that the data from the code was linear, which is important, and that the data from Tracker was actually quite linear, not exactly, which we'll get into in the next section. The fact that they lined up meant that the experiment was quite accurate. So what are some possible sources of error? What made the experimental data nonlinear? Well, friction was present. Because the table caused the marker to roll, we know that friction was present. Air resistance was present because the marker slowed down. And the table could have been slightly sloped, which could have caused some error as well. So what if the axes were to be inversed? This would simply make the results the same, just in a different direction. And what does this mean? Well, we can add together the pushes and pull that make this specific case have net zero force if we only consider the forces that have tangible effects, meaning that we're not taking into account any forces of other planets in the solar system that may not have infinitesimally small forces on the marker. Thank you.